Okay, so welcome to our PD reading seminar. Today we have Junyuan Fang, who is currently a PhD student at UTK under Tuc Phan. He's gonna talk about the basic but important Harnack inequality for singular or degenerate parabolic equation in non-divergent form. Please, Junyuan.
Okay, thank you. Thank you everyone for coming, for showing up, and especially thank Professor Han Zhuang for giving me the chance to do the presentation here. Yeah, so today I'm going to talk about some Harnack inequality for singular degenerate parabolic equation in non-divergent form. And this is a joint work with Sungwon Cho, who is a professor in Gwangju National University of Education in South Korea, and with my advisor, Tuc Phan. Okay, let's start. So firstly, here is my outline. Today's outline. Firstly, I will review some Harnack encoded in different PDEs, and later on, I will introduce our problem setting and the main results. So we have two. The first main result is Harnack encoded, and two colors. One is Holder regularity, one is Lewisian. Okay. After that, I will introduce the key steps in the proofs. It based on three growth lemmas. Okay. So let's start. So firstly, we know Harnack encoding is very important. You can think Harnack encoding is a quantitative version of the strong maximum principle. So the story goes back to 1887. And Harnack did some research on the harmonic function like in 2D. Okay, so it's the analytic function in complex analysis. So, but later on we can generalize to any dimension n. So this one says there exists some n depend only on the spatial dimension little n, such that if U is a solution, is a non-negative solution, non-negative harmonic function, that means Laplacian U equals 0 in B2. The ball was radius 2. Then the supreme of U in B1 will controlled by some constant n times the infimum U in B1. Okay, this is a well-known result. And the key in the proof is just by we know harmonic function has the mean value property, and use this one, you can easily, we can get Harnack. Okay, so this is some familiar results. So let's move to some parabolic case. So this one is Harnack encoded for caloric functions. Caloric function is just means the solution to the heat equation over here. Okay, it's in 1954. Pini and Harnack, they independently found that there exists some n also depend on the spatial dimension little n and 0, such that if U is a non-negative caloric function, okay, so satisfy this heat equation in this cylinder, okay, say 2, and then the supreme of U in U1 will be less than, will be controlled by some constant n times the infimum of U2. So this Harnack for is a little bit different from the elliptic case. Okay, so I draw a picture over here. So we have one cylinder like this guy. If we think this one is a original point, the radius is 2, then the height is 4. Okay, the height of the cylinder is 4 because we have the parabolic scaling. So here's r, here will be r squared. Okay. And if we consider the interior half ball, like the region, right? Spatial region is the half ball B1, and we divided the time interval into 4 pieces. Then we have 4 quarter. U1 will be the signal quarter, right? If we consider there's something. So this will be the signal quarter, and U2 will be the fourth quarter from the bottom to the top. Okay. Over here, like this one. And this is so you will find this, the region is different from the harmonic, the elliptic case. This is B1, right? they are the same, but here they're disjoint. Okay. So you can think the space, but the spatial region is the same. Okay, the time is disjoint. So there's some remark. So for this form, Harnack, the time gap between U1 and U2 is necessary because Morse give an example is that if Uxt equals e to the lambda t, lambda squared t plus lambda x is the is the solution to the heat equation in 2 dimensions. Okay, then if you think this U1, U2 is the same interior region, or they are just next to each other without the time interval. If you let this lambda go to infinity, this n will blow up. So it's not Harnack. So we need the time gap over here between U1 and U2. And how do we think about this this conclusion? You can think this is the heat diffusion model. U is a solution. U will be the temperature. Okay, you can think U is the temperature, and this is a heat diffusion model. The right hand side is 0. That means there's no heat source inside the cylinder, or there's no reaction term. So if the supreme U is big in U1 is bigger than 0, that means there's some heat in this region, right? Bigger than 0. And we move this n to the left-hand side. There will be 1 of n super U less than the infimum. I mean, infimum is bigger than this guy. So if there's some heat over here, after some time, everywhere in U2 is occupied with the heat, with a uniform lower bound. Okay, intuitively, if you want to achieve such results, you need some time for the heat to pass or to diffuse. Okay. So in parabolic case, we always use this picture to help us understand the Harnack. Okay, so let's go to some other things. A very important thing for the previous one is that the Laplacian, the diffusion matrix is the identity matrix. So that means it's smooth, it's very good. But let's talk about some non-smooth diffusion coefficient. Here is the most Harnack encoded for parabolic equation in non-divergent in divergent form. So here is the equation, and we assume the diffusion matrix Aij xt is only measurable and bounded and uniformly elliptic. Okay, we don't need some regularity assumption. Okay, it doesn't have to be continuous here. Here nu is the ellipticity constant. That means satisfied by this condition, and it means the eigenvalue of Aij is bounded from below and from above for all the points in the cylinder. Okay, so in 1964, Morse says there exists some n only depend on the spatial dimension little n and the elliptic constant nu, such that if U is a non-negative weak solution to this equation, then the supreme U in U1 will be bounded by this constant times the infimum U. So you can still use this picture to help you understand it. The conclusion is the same, but the equation changes. So the idea or the technique to prove that is very different. Okay, so I also put some remark over here. DeGeorge, Nash, and Morse, they independently proved the Holder regularity to the uniformly elliptic equation in divergence form, and this is known as the DeGeorge, Nash, Morse theory. And this is very important because because of DeGeorge and Nash, the Hilbert 19th problem was solved, and also this technique, the DeGeorge integration or Morse integration can apply to the quasi-linear equation. So that's a very powerful technique. Okay, so here a very important thing is Aij is uniformly elliptic. So let's talk about some results doesn't satisfy uniform elliptic or degenerate case. Okay, so let's talk the elliptic divergence form, but Aij is degenerate or singular. Okay, let's do some positive conclusion. So most for elliptic case, so the Harnack will be this form. If AIG Schrödinger in 1971 says if AIG satisfies some integrability condition on the smallest eigenvalue or the smallest and the largest eigenvalue lambda, little lambda, capital lambda of AIG, that means little lambda to the -1 in LP, capital lambda in LQ with 1 of P plus 1 of Q less than 2 of N. This N is a spatial dimension. Then you still have this most Harnack. Okay, you don't need the uniformly elliptic condition. But here, their N is in some sense depend on the behavior of the integrability behavior in this ball. Okay, so in some sense, it's not so generic, this constant N. Okay, later on, in 1982, Fabs, Koenig, and Saprini, they said if this AIG degenerate like this way, so we have some omega x over here. Okay, if this omega x belongs to A2 Mann-Hope class, this is some functional class. The function can goes to somewhere can goes to 0 or goes to infinity. So it's not the it can be degenerate or singular. Okay, they say under this condition we still have the most Harnack, and the N is generic. That means independent of the solution and the position. Okay. And also in 2021 recently, Bala and Schaffner, they did a resolution to Schrödinger's results. They say that the upper bound, this guy, okay, can improve to 2 over MS1, and they show less sharp. Okay, so this is some elliptic case in divergent form and the degenerate. Let's talk about some parabolic. Okay, it's still parabolic divergence, but AIG can be degenerate. The story is very different from elliptic. In 1984, Chialanza and Sarpini, they said no most Harnack if the constant, right, the N is within the independent constant. Okay, on the no most Harnack under any type of AP conditions or Schrödinger's results on the weight, as in the elliptic case. They construct a couple examples, says no most Harnack. Okay, and 1 year later, they claim like most Harnack holds true for some non-standard cylinder. So over here no Harnack, most Harnack, that means their cylinder is with radius r, the height is r squared. Okay, that's the regular cylinder. But here they proved that this guy holds true on some non-standard cylinders under some strong integrability condition on the omega to -1. Okay, here are some results for degenerate or uniformly elliptic in divergent form. So here another story is Ivan's Krylov Harnack inequality. Since we introduced, my talk is basically on parabolic case, so I show the parabolic version of Krylov-Safanov. Okay, so UT minus AIG DIG, U equals 0 in this cylinder. AIG still satisfies the uniformly elliptic condition. It doesn't have to be regular. Okay, so in 1979 and the 1980s, Krylov and Safanov proved if U is a non-negative solution to this equation, then supreme U in U1 will less than some constant n times the infinity of U in U2. So here the solution for this equation, that means it satisfies the equation almost everywhere. Okay. And this one is also very important. This series is very powerful. Let me put some remark over here. Because Krylov-Safanov Harnack inequality, Evans and Krylov, they showed in 1982 and 84, they independently showed C2 alpha for some fully nonlinear elliptic equation on the F is convex or concave. Also, Cavalari in 1989, they generalized the Krylov-Safanov Harnack to the elliptic equation in physicality sense. Okay, so physicality. And Li He Wang in 1992. Here also physicality sense, but there's Cavalari is elliptic, but Li He Wang is parabolic. Okay, so that means Krylov-Safanov theory Harnack is very powerful. Okay, so another remark is that to best of our knowledge, if this AIG becomes degenerate, there are few results concerning the Harnack equality for the degenerate parabolic equation in non-divergent form. I mean, here few if we put some weight omega in front of AIG, and we couldn't find much results. So that's our motivation. Okay, so let me come to my the problem setting. Okay, of here, our problem setting for simplicity, we just consider the diffusion term without the lower derivative. Okay, L U equals UT minus omega x times AIG. So we just simply put a weight of here. Okay, so you can think the example is the UT minus the He equation with some weight here, and this omega is a weight. It's called a weight. It should be non-negative and measurable and locally integrable. Okay, AIG still is the uniform elliptic. So this is called the degenerate or singular because if we take the product, right, this term, okay, is not doesn't satisfy the uniform elliptic anymore. Okay. Another remark is that if omega equal 1, this L is reduced to uniformly parabolic operator. Okay. So there's a natural question is that what assumption on we put on this omega, like issue the Harnack inequality holds for the solution. Okay, that's our motivation. And also I want to emphasize why we do care for the parabolic case instead of elliptic case. Because if without this term, you think the elliptic equation in non-divergent form, you can simply divide it by this guy, right? That's equivalent to the uniform elliptic. But if we consider parabolic equation in non-divergent form, if you divide it by omega x on the both side, then this guy will be 1 over omega. It's still becomes singular. Okay, so that means for elliptic case, the divergent form doesn't make sense. Okay, so let's go to yeah, here is our results. So let me introduce our result first. So for example, if we let the capital Y means the point in the little y times comma s, this little y is the spatial space, s is the time. Okay, the little r is bigger than 0, that means the radius, and our L is the operator is this guy. Okay, so our Harnack equality basically says for every genetic k naught bigger than 1, there exists some epsilon depending on the spatial dimension, the elliptic constant, and this k naught. This is small, and this n also depend on these 3 parameters, such that if this omega satisfy this condition, so far I haven't introduced this one, right? This is some A1 plus 1 over n Monkenhoop class. Okay, this you can think this is the first condition, and also the second condition is the BMO on this ball with respect to omega is less than epsilon, this epsilon. So so far you can think this is the second condition we put on omega. And then if U is a non-negative solution to this equation in this cylinder, So after this radius, we put a mu over here. That means this is some new type weighted cylinder. Okay, I will introduce it later. Okay, then we have the Harnack. This Harnack, the parabolic form is the same. Okay, you can use the previous picture to help you understand that. So we have something new is we have two assumptions on omega, and we have a new type cylinder. Okay, so I draw a picture here to, yeah, it's the same. So if we have the cylinder over here, this is 2R. The height, I put another term over here, okay? Later on, I will introduce. So U1, U2 is the corresponding the second quarter and the fourth quarter over here. That means if you have some heat in U1 positive, right? Then after some time, everywhere in U2 is occupied with the heat. Okay, that's the physical understanding. All right. So next one, let me introduce the weighted parabolic cylinder firstly. Okay. If we fix y equals y comma s, little r bigger than 0, and mu, we define mu to be the omega to the negative n. Okay, we introduce a new function, and we denote the average of mu on the ry is the integral of this guy, right, of mu, then divided by the bigger measure of this ball. So let's recall some uniform parabolic cylinder, okay, in the textbook. We know for parabolic equation, we have the regular cylinder is if the spatial radius is r, then the height of the cylinder will be r squared, like this one, r to r squared. Okay, and how do we come up this term? So you can basically think this also is the heat diffusion model. We know AIG is the diffusion flux rate. Right now, if we have the omega between 0 and 1, right? So it kind of says your diffusion rate is kind of small. So the diffusion, the heat is less active than the regular one. So in order to achieve some point, right? In order to achieve the same temperature increment or decrement, you need more time. Okay, so that means the heat and the height will be taller than the regular one. Here, if omega less than 1, this mu will be bigger than 1. Then the average will bigger than 1, so it's taller than the regular. Okay, the same idea, if omega bigger than 1, that means the heat diffusion is more active. In order to achieve the same temperature increment or decrement, you may just need less time. So we put, if omega bigger than 1, this term will less than 1. Okay. And the power of n, I will introduce later. This is for some technical stuff. Okay. For this slide, we just basically introduce a new cylinder, weighted cylinder here. I put a mu over here, basically says we have this term r squared to the average on bry to the 1 of n. Okay. All right. Let's come to the first assumption on omega. Okay. Here we need the omega and the weight in some A1 plus 1 or 1 of n class. This is some Monkenhope class. Let me give the definition. You may not familiar with this one. If sigma is a non-negative locally integrable function on Rn, we say sigma belongs to the A1 plus 1 of n Monkenhope class if this number is defined by, you will see this guy, the average of sigma on this ball, right, below x naught, times the average of sigma to the negative n on this ball to the 1 of n. Okay, we fix below the ball, then take average, take this term, right? And we take the supreme of this quantity. If this quantity, the supreme of all balls, is less than infinity, we say sigma belongs to A1 plus 1 of n, Monkenhope class. Okay. Honestly, you can also define for any p bigger than or equal to 1, but since in our paper, we just need this index, so I give the definition like this one. Okay. So our first assumption is that we need omega in this A1 plus 1 of n. And the same for some given k naught, right? We need our omega, the Monkenhoped characteristic number is less than k naught. Okay. There's some remark is that since we define mu as omega to the negative n, by this definition, if we replace this sigma by omega, this term will be omega. Then sigma to the negative n will just be mu. Okay, so we have this quantity less than the characteristic number for every ball, right? Also, the left-hand side bigger than 1, you can simply buy the Holder inequality to get this quantity, okay? It has a lower bound bigger than 1. So we will use this one in the proof later on, okay? All right. If you have any question, you can stop me anyway, okay?
Yeah, I have a question. I mean,
Okay,
because a lot of people who are not familiar with Mückenhof class, then basically
okay.
what you say is that people only need to remember this inequality, right? They can forget about the definition.
Yeah. They can forget about definition. We just need this one.
Okay.
Yeah. Thank you. Yeah. All right. Let's go to our second assumption. Based on the previous condition, we also need omega satisfy some weighted BMO condition. So here's a definition. If we already assume omega in A1 plus 1 of n, f is some integrable function omega on R to the n, we say this little f is of weighted bounded mean oscillation with respect to omega if this quantity defined by over here, right? You will consider this guy first. If we take the integral of f minus the average of f on this ball to the n plus 1 times omega to the negative n. So this is some weight, right? Once we take the integral, we divide it by the omega measure of the ball. Omega measure is defined by just the integral of omega in this ball. Once we have that, we take the 1 of the power 1 over n plus 1. Then we take the supreme of all this ball. So that means it's a local condition. Okay, all this ball. If this supreme less than infinity, we will call this is mean oscillation. Okay, weighted mean oscillation with respect to omega. But I cheated a little bit, right? Mean oscillation usually this power is 1. Okay, but I will introduce later on. The second assumption, if we have this definition, the second assumption is that for some given k naught, the k naught is this k naught try to control this guy. Okay, we have some optional dependent on n, nu, and k naught is small, such that if we replace, if we put omega into this position, right? So the weighted mean oscillation with respect to omega of omega is less than optional. Okay, we need this condition. There's some remark is like why we call this guy's weighted mean oscillation, because in Monkenhop's some paper, he claimed that this quantity, so the power here is n plus 1 negative n, you can generalize to q, right? Q 1 minus q. And he said every q between 1 to negative n plus 1, they are comparable. So over here, this is n plus 1, right? But if we replace this by 1, this is 1, then this guy will be 0. So this is 1 later on. So everything here becomes the mean oscillation in classical sense. So that's why we call the weighted bounded mean oscillation instead of like a mean oscillation to the n plus 1 stuff. Okay, but in our paper, this condition comes naturally, so we keep this form. Okay, this some remark. All right. let's go to next one. All right, let me come back. So I introduced these three, right? And the slant cylinder, no, sorry, the parabolic weighted cylinder, the assumption 1 and assumption 2. So we have this Harnack, right? But since we put two assumptions on the weight, we do hope if you take the intersection of these two assumptions, we have some, it's not empty set, right? So we need some example to support our theory. I introduced two examples. One is trivial, one is non-trivial. The first example is omega equal 1. Then we basically have, we know the A1 plus of n from harmonic analysis, we know this is 1, so less than k naught. And the bond, since it's a constant, okay, so the oscillation is 0, so that's the option. Okay, this is good. The second example is that if we omega equals x, the modulus of x to the beta, if beta is very small, so this one can be degenerate or singular. On one hand, we know from harmonic analysis, if beta between negative n to 1, we have this guy in this class. Okay, this is some no results from harmonic analysis. And also, if we restrict our beta in negative 1/2 to 1/2, there exists some constant, okay, depending only on the dimension, such that this characteristic number is less than this uniform constant. On the other hand, we can just by calculation or carefully calculation, this bounded weighted mean oscillation of this function is less than some constant times the power. Okay, if the power goes to 0, this weighted bounded mean oscillation will go to 0. Therefore, for this given k naught, right, and also optional depending on this k naught, we basically let this beta goes to this absolute value kind of small, then at the same time satisfy the assumption 1 and assumption 2. Okay, so that means if your beta is kind of small, the weight will kind of like this one, if almost like a constant. This is beta bigger than 1. If beta less than 1, they will be like this one. It's only singular or degenerate at a very small measure. Okay. All right. Let me go to the next one. Okay. Before showing the proof of Harnack, let me introduce two corollaries. Okay, and their proof. The first corollary is called hold regularity. There's something new over here. The series for every k naught, we try to control the AP, the A1 plus 1 of n number. There exists some optional depending on these three parameters, small and alpha between 0 and 1 and constant n, such that if this omega, the weight, right, satisfy the first condition, the second condition, then U is a bounded solution in this weighted cylinder, okay, to this equation. We have the whole regularity estimate. So here is the whole semi-norm, but I treat it a little bit. This is something new, okay? This is called the weighted whole semi-norm, okay? This guy will less than n times r to the negative alpha times the L infinity norm of U. So I didn't introduce this one. Basically, usually if you have the Harnack, you can get say alpha by the standard way. But because here we introduce some this is a degenerate case, so we need to introduce some new matrix, okay, connect to the weight. So let's come to we introduce a quasi-matrix. This is some new stuff also. The idea is that if we have 2 points in the spatial time space, y equals this guy x, and we may assume s bigger than t, so that means y is taller than x. And we define this hy tau is the height function. You can think if we fix this y, right, over here, the little y, So tau is the radius. You can think the radius variable. If we make this as the variable, then the height of the cylinder will denote h tau. Okay. The second one is that the capital theta y of x. This is the infimum of R, such that this x will in this cylinder. Okay, so the idea is like this guy is increasing with respect to tau. Okay, so if the spatial radius is bigger, the height will be larger. Okay, so basically, how do we make understand this one? You can think we fix this y, fix this x. We basically let this tau bigger, this bigger, larger, right? You will have a larger cylinder. Okay. At some time, the first radius r, the boundary will hit x, right? It's kind of like in probability, like the stopping time, the first time. Here is the first radius. But we don't know which side it hits the x, right? We have two cases, either the lateral side hit x or the bottom hit x. So we have two cases, okay? And how do we introduce the new matrix? We basically try to take the same as the spatial radius, y minus x. So let me put something over here. If for the regular distance between x and y, we know this guy square equals x minus y square plus t minus s, like this one, right? So for ours, we try to keep this the same, but t minus s, we times this term to the negative one of n. We take it back. Okay, so kind of like low omega capital X, y will be x minus y squared plus mu, sorry, it will be t minus s times mu to the b, this with this guy, to the negative one of n. Okay, so if you do more carefully about the calculation, we will have this form. This is a weighted, this is our matrix. And you can symmetrize this guy. And also this is non-negative. In the other, another remark is that this is not a matrix because it doesn't satisfy the triangular, but it is a quasi-matrix. It satisfies the weakened triangular encoding. So instead of 1, here is 2. Okay, you can basically by some calculation show this property. So this is a quasi-matrix. Based on this quasi-matrix, we define the weighted whole seminorm. It's just the same as before, the classical one, but we replace this distance by the quasi-matrix. Okay. So once we have this one, we can prove the C alpha estimate. Okay, here's the proof. And the idea is basically the same as the classical one or the uniformly elliptical one. So we introduce the supreme in some cylinder and the infimum, and we take the oscillation with the variable is tau. We apply Harnack inequality to this guy. This is non-negative. This is also non-negative. And later on, by carefully computation, you will have this oscillation controlled by this number. And by iteration, since this is a nested cylinder, okay, you will get the oscillation decay. You will see this is less than 1. This term also less than 1 for every k positive integer. So this one basically implies the whole regularity. And for better understand, I draw some picture here. So this is the oscillation. We know oscillation, if we fix the center, right, then we like the variable is the radius, the spatial radius. We try to think the oscillation function over this cylinder. Okay, so we know oscillation is non-decreasing function, decreasing function. That means there's some function like this one. This is the oscillation function, and this step function offers a upbound. of the oscillation. And because we want to get the C alpha estimate, we basically hope there's some x to the alpha upper bound. A natural, because of this specific oscillation decay estimate, you can simply connect all the vertex over here. So that's this one. And based on the oscillation, we have this form. The purple curve is y equals n times x to the alpha. So this alpha will be the Holder index, and this n is something related to the upper bound. Okay, this is the basic idea. All right. So the next one is Liouville theorem. Liouville theorem says for every k not bigger than 1, they also the same assumption optional, right? If omega satisfies the first condition and the second condition, and U is a bounded solution over the whole space, the spatial space, and the time is from negative infinity to 0. So right now you can think U is the entire ancient solution. Okay, it's a bounded entire ancient solution to this equation. Then U has to be a constant. Okay, and the proof is basically from you can use the oscillation argument. This can go to infinity, right? Keep going. And we also know U is bounded. So by the unboundedness of the domain, this force the oscillation has to be 0. Then U has to be a constant. That's the basic idea. Okay. So, all right, we finished about the corollaries. Let's come to okay, I don't have much time, but let me show the outline of the Harnack theorem. Okay, for classical way, in some textbook or a standard way, one standard way to prove Harnack is by consider two sides. The first one is consider the subsolution. If you have the L infinity to estimate to the subsolution, and at the same time you consider super solution, you will have if you have the so-called V Harnack or L optional estimate, then you combine these two, you will get Harnack. But for Krylov-Safanov, the original idea is they didn't derive these two estimates. They tried to get some Galois lemma, but essentially the idea is the same, similar. And by some other technique, you can also get Harnack. So for this slide, I just say in our paper, we didn't try to derive the V Harnack, but the idea is kind of similar. Okay, so I basically introduced the Galois lemmas. Okay, so the first okay, so here is the basic tool we use in our proof. Okay, this is called the Alexandrov-Krylov-Tissot estimate. This is a parabolic version of the ABP estimate. So I will quickly show the idea, okay, over here, because there's some geometry interpretation behind this one, but I don't have much time. Let me just quickly show this one. If we have omega is some domain in Rn+1 in this vertical cylinder, okay, and U is a subsolution, and if U on the boundary is less than 0, parabolic boundary, then the supreme U will bounded by this term n times R to the m over n+1 to the F positive to the Ln+1 now. Here omega plus is some positive region, okay, and we have this guy, okay. All right, let me move to this estimate is very important in our proof, and it is very well known. This is parabolic version of APP estimate. Our first Galois lemma is over here. If we simply assume y equals is the original point, and this is the weighted cylinder, the measure we denote by mu omega. Okay, this integral. Our first Galois lemma, it says if k not bigger than 1, optional less than is some quantity between 0 and 1, delta not is also 0, 1. Like this n depend on n u k not such that the first condition, the second condition. And if u is sub-solution in this one with the positive parts. The measure of the positive parts is less than delta naught, or the density of the positive part is less than delta naught. Then the supreme of U in the CR mu, okay, here's interior. Let me draw a picture over here. This is the C2R mu, right? And also I try to draw an interior cylinder like this guy. This one is the CR mu. Okay, so we know this is sub-solution. So the maximum has to the strong maximum principle tells us the maximum of this U, right, has to achieve on the parabolic boundary instead of interior. So this property, this first growth basically is a quantify. This guy has to be smaller than this one, right? How smaller compared to the maximum? Okay, this is independent of the solution. So it says if omega epsilon is very small and this delta naught is very small, that means there's some region that all this shaded region is U. There will be U less than 0, right? So if this delta naught very small, then U less than 0 will be very large portion. This small, this epsilon small, delta naught small, this guy will less than 1, right? So it's a independent quantity. So it basically says how smaller compared to the boundary if we know the density of the interior, bigger than 0 parts. Okay. So I will use the proof of this lemma to basically show the idea how we came up with these two conditions. Okay. So let me quickly show this one. Okay. For simplicity, we only need to show on the center, okay, less than this quantity. So the right part is kind of like a Berry function. We construct this Berry function. Then we have this phi on the parabolic boundary is less than 0. We apply the operator to this function. By the perturbation of this one, we have the omega average, right? And the acceleration term. And also by the condition, the density condition, we have these two, this condition. And apply the Alexandrov-Krylov-Tissot estimate to phi. We have this term, and this is the first term, this is the second term. Okay. So the first term, if you do calculation carefully, you will get this guy. Okay. And this is Professor Hen Chuang said. This one, we only need this guy. The A1 plus 1 of n quantity less than K naught. Over here, we use this quantity. And the second term, by carefully computation, we will have this, we need this quantity. We try to make this small. Okay, so that means the acceleration is very small. We need this one. Combine these two, we have this condition, this conclusion. Okay, this is the first growth lemma. It basically says if you have larger portions less than 0, right? Larger portion is less than 0. Then also the acceleration is very small. The interior half cylinder will smaller than some uniform constant, okay, to the supreme of the ball. So it's a quantitative of the maximum principle, the strong maximum principle. Okay. Then the second one is signal growth lemma is on the stand cylinder. It basically is the motivation is that if we have some information on the base, right, we try to estimate after some time the spatial region moved away after some time, right? Based on this some information on the base, we want to estimate some information on top. Okay, so this is the definition of the slant cylinder and our parabolic cylinder of this this slant cylinder is the lateral and the base, okay, except the top one, okay. Also, you can think we try to estimate after some time on the top, right? So you cannot expect the region over here, the spatial region over here, but after very short time, you want to estimate very far away region, right? We cannot expect that much. So we need to put some assumption on this slant cylinder. We cannot make the slope very big or very small, like very slant. We don't want like cylinder. Okay, so we put this condition is called the K slant. It satisfies the slope condition, also satisfies some scaling invariant property. Okay, this condition will be used. All right, let's go to this guy. So this closed lemma on slant cylinder says for this k not bigger than 1 and k bigger than 1, like this epsilon 1 based on this property quantity beta 1 0 1 such that on the slant cylinder, if this 1 satisfies k slant condition and omega satisfies the first condition and the second condition, then U is a solution, sub-solution on the slant cylinder, also on the base, right, is less than 0. We assume this term t equals 0, the base is less than 0, okay? Then we have the supreme on the top, the half ball, okay, the region, half ball at S, t equals S, will less than beta 1 times the supreme of the parabolic boundary. That is also equivalent to the by maximum principle we know is the max supreme of the slant cylinder. Okay, this beta 1 is between 0 and 1 and is independent of the solution U. So it's also a quantitative version of maximum principle. Okay, so the idea and the proof, let me quickly show the proof. Okay, so we also introduce some test function like this one. Then we apply the operator L. We apply the perturbation technique over here. If you after some calculation, you will get this term and this term. And for this term is a quadratic right function. So if we choose lambda very large, so this lambda is to determine the later. Okay, so over here we choose a very large lambda, so this quantity will less than 0. Okay, so we only have this guy. Then we try to construct some binary function. So this is the binary function, and then we take the difference between this one. So that this new function on the parabolic boundary is less than 0, and because of this one. Okay, then we'll apply the operator L to this capital phi. We'll get this guy and apply the Alexandrov-Kirov tensor estimate. And using K slant, we will have this condition, right? Well, we assume this one too. So this is where we came up with the condition, this condition. And finally, if we choose this epsilon small, we will have our conclusion. So I want to do some remark over here between first closed lemma and the second closed lemma. If you come back, you will see the first closed lemma and the second. Oh yeah, sorry.
I think you should finish in 1 minute.
Okay, yeah, sorry, yeah. Over here, I want to say the closed lemma, first closed and second closed lemma, they're independent, but we came up the condition, the same condition appears. Okay. Also, we have one more closed lemma. It basically, let me quickly show one proof, the graph. Okay. Let me use this one. If we satisfy the condition, the first condition and the second condition, this says if we have information on this Q, then we have the information of this the top cylinder. Okay, so that means if we have some density, positive density of this Q, then the supreme of the interior half ball, half cylinder will smaller than some beta 3. Also the independent of solution between 0 and 1, the maximum is also a maximum principle, the quantitative Okay, so for the proof, this proof is basically based on the covering lemma. This one, Krylov and Safonov show this one in their original paper, but we just adapt the proof to our weighted setting. Okay, and this is the recall. Okay, so we basically show this one, and by some introduce a distant function, then we still have the Harnack instead of to derive the V Harnack. Obviously, we have the L infinity in our paper, and yeah, we still get the Harnack. Okay, yeah, that's all. Thank you.
Thanks a lot for your talk. We will have our informal discussion soon, but is there any quick question for Yunyuan?
Can I ask one?
Yes,
Yeah,
please.
yeah, yeah, please.
Yeah, so I seen like more in a more differential form of the Harnack inequality, like the maybe Liao type. So I'm
Yeah.
not sure like whether this is like related. So it's like they usually construct a quadratic a negative quadratic form and then use maximum principle to show that it remains non-negative so that the discriminant is non-positive, and then they get some type of differential type of Harnack inequality instead of this supreme inframe form. So I'm not sure like
Oh yeah, I forgot to say our Harnack is the interior Harnack, right? It's the interior Harnack. So you said, yeah, they also like a boundary Harnack encoded. I'm not so sure whether the one you talk is about the is that interior the parabolic version?
so I think it's interior. So it's usually like manifold without boundary or so.
Oh, on manifold, right?
Yeah, yeah.
Yeah. Yeah. So our Harnack is based on the Euclidean space is kind of flat, right? But for manifold, I don't
Okay.
much about that. Yeah.
So like if the equation is like is still it will locally look like the same equation you mentioned, like in
Okay.
non-divergence form.
Oh
It's
yeah,
still
yeah,
a
yeah,
parabolic
yeah.
equation, but then it's just like locally
Right, right,
yeah.
right, right. Yeah, yeah. Locally is the Euclidean space. Yeah, sure. Um. Yes.
That's actually a great question. I think we can talk because the time is off, so we
Oh, my
can.
bad.
Yeah,
Sorry.
no. I mean, not a problem at all. The time is correct. I think that we can discuss more on the growth lemma and then whether it's possible to adapt it to manifolds or not in our informal discussion. Okay. So thank you for question. Uh, okay. I think that we should stop our formal talk. So thanks, Yun Yuan, for a very interesting talk. Okay. So let me